So last time we constructed the tensor product of two modules. So let's work in the setting of R is a ring and we have a right module and a left module. So this is a right module, N is a left R module, and given these two ingredients we define something called the tensor product of M and N over R, and this tensor product finally had the structure of a Z module or abelian group. Recall also the key fact that we used while constructing this tensor product is that there is an important map from M cross N to the tensor product, okay, which we called alpha, which takes each pair M comma N to, well, a certain element alpha of Mn, and the notation for that element was M tensor N. Okay, so this was just notation for the image of Mn under that particular map alpha which we constructed. And the key point about such elements is that well, not all elements of M tensor N can be written in this form. Okay, the image of alpha is not all of M tensor N, but it's rather close, meaning the sort of the span of these over Z will give you everything in M tensor N. Okay, so every element, so each element, every element of M tensor N can be written in the form summation Mi tensor Ni. Okay, I goes from 1 to k. Mi, Ni, Mi come from M, Ni come from N. Okay, so it's a finite sum of such things. This is not necessarily a unique expression. The same element can be written in many different ways. But what this says is that these elements of the form M tensor N, they sort of generate the group over Z. They generate the abelian group M tensor N, if you wish. Okay, so often when we want to prove many things, it's enough to sort of prove it on the generators. Okay, so we have constructed the Z module M tensor N. The goal of today's lecture is to see what happens when you have maps or functions or homomorphisms of M and N. Okay, so suppose I do the following: given R linear homomorphisms, given R linear maps. Okay, so what am I going to give you? A map from M to another right module M dash and G from N to N dash. Okay, where what are these? M dash is a right R module, and N dash is a left R module. Okay, so now and what is an R linear map? Well, it's the usual definition also for right modules. It just says that if I have f of so aside what is, so in this case what is meant by a right R module homomorphism, it just says if I have f of mr, then this is nothing but f of m times r. Okay, now this should be true for all m into m, for all r and r. Okay, so such a map from M to another right module M dash is said to be an R linear map or a homomorphism. Okay, so an F which satisfies this and the other property, the linearity. Plus Fm2. This is true for all M1 and M2 in M. Okay, so such a thing is called an R linear map. So this is R linear. So same definition as you would give for left modules, okay, except that everything acts on the right. Okay, so given two R linear maps from M to another right module M dash and from N to another left module N dash, there exists a unique, well, now it's a Z module homomorphism. There exists a unique Z linear map. Okay, and this map is from, let's call it something T for now. It's a map from M tensor N over R to M dash tensor N dash over R. Okay, there's a unique map satisfying the following property, that on those generators, the elements of the form M tensor N. So sometimes such elements are called simple tensors or decomposable tensors. So on a simple tensor M tensor N, T takes the following value. It's just given by the product, well, the tensor product f of M tensor G of N. Okay, so the claim is, given two maps F and G, you can construct a third map T which has the following action on the generators. Now the point is, to prove a fact like this, you can't just start with this as the definition. So starting, just suppose we say, okay, let's define T like this. Let's take elements of the form M tensor N and define T in this manner. The trouble then is showing well-definedness, okay, because the M tensor N's, the decomposable or simple tensors, they are, they generate the module, but a given element of the module M tensor N could be written in many different ways as a sum of Mi tensor Ni. So if you define it in this way, then you will be stuck with the problem of showing that no matter which way you take of writing that element as a linear combination or as a sum of Mi tensor Ni, the answer gives you, would be the same. So that's sort of messy, and we would prefer not to do it in that manner. Okay, so it satisfies this property for all these guys. So in other words, i.e. on a sum like this, what we mean is that T has the following property. On such a sum, it maps it to this. Okay, so like I said, this is the final property that we want T to satisfy, but we cannot start with this as the definition, because then we'll have to somehow show well-definedness. Okay, instead we'll do this indirectly by using the universal property of the tensor product. Okay, so proof, let's use the universal property. Okay, of the tensor product. So tensoring over R of two modules. What was the universal property? Well, it said the following. So if I take M tensor N and I define a map to any other module which is Z bilinear, then there exists a unique map from the tensor product. Okay, so I should also take these R balanced maps in this case. So let's do the following. So let's take M tensor N over R. So I'm doing everything over R here. So let me consider the following map. Okay, from M tensor N, I can define a map to M prime tensor N prime first. Okay, so how am I going to define that map? So we'll come to this next. So how am I going to define this map? I will take a pair M comma N and map it to f of M comma G of N. Okay, now from here, of course, I already have a map to M prime tensor N prime over R. What's that? That's the corresponding map alpha prime for the tensor product. In other words, this will take this to the element Fm tensor Gn of N dash. Okay, so let's give this guy a name. So this is just some map H. Now consider the composition of these two guys. So consider alpha prime composition H. Okay, now where is this a map from? It's a map from M cross N to this module M prime tensor N prime. Okay, I claim that this map is R balanced. Okay, alpha prime composition H it's R balanced. Okay, so recall R balanced meant that it's a usual Z bilinear map, but also it has that property with respect to scalars from R. Okay, so let's prove that it's R balanced. So first thing we need to show is that this is Z bilinear. So let's do that. So let's take alpha prime composition H, evaluate it on M1 plus M2 comma N. Okay, it should split into two pieces. So let's try this. So this is alpha prime of f of M1 plus M2 comma N, comma Gn by definition of H, and this in turn is just because f is given to be R linear, it's going to be this sum. So this is now all this is happening inside M prime tensor N prime, and there of course this tensor product symbol is bilinear, right? So we know that this is just going to give me fm1 tensor Gn plus. Okay. So the first property is satisfied. So we have checked that this satisfies the bilinearity in the first component, the linearity in the first component. Now similarly the other one, so let me just leave this as an exercise. This is just equals alpha prime composition H. Okay, it's the same proof more or less. Now the third one, the R balanced, is what we really care about. That's the new thing here. So let's check this. Okay, so what are we going to do? We are going to check the following. Suppose you take alpha prime composition H, you take an element of M, you take an element of N, but let's do the following. Let's put an R here. So let's right multiply M by an element R from the ring and see what happens to this. Well, by definition, this is alpha prime of f of MR comma Gn, but f is R linear. Recall that just meant that I can put fmr comma Gn, and again this is fmr tensor Gn. Okay, but now recall that this tensor product over R, right? Remember we are doing all this over the ring R, right? That we are looking at that tensor product. And so this element here, so alpha prime, the map alpha prime itself was R balanced, right? In other words, this R can be moved from here to here. That was more or less the defining property there. Okay, so what that means is that this is Fm tensor R Gn. Okay, but again now G was R linear, so that R can be further pushed inside. Okay, this can now go further into the N. So this just becomes Fm tensor G of Rn, which is exactly what we needed to show. This is alpha prime H of M comma Rn. Okay, so what we have used here really is just the fact that the tensor product over R is an R balanced map. Okay, good. So what this means is that the three properties we need are true. So we had a map M cross N to, so maybe this is a good way to draw the diagram. So from here have this map. So this is alpha prime, this was H, and alpha prime composition H was R balanced. So by the universal property, okay, so alpha prime H is R balanced. Therefore, by the universal property, so I'll abbreviate it to UP, there exists a unique map. Well, this is now a Z linear map. It's a unique Z linear map. Let's call it T from M tensor N to such that this diagram commutes. So there is a map here T such that the diagram commutes. So in other words, T alpha is the same as alpha prime H. Okay, so this just I'm using the universal property of the tensor product. But then observe, this is exactly what was given in the proposition. So T alpha just means if I take T alpha of M comma N, is therefore the same as alpha prime h of mn, okay, for all m in m, n in n, and this is just the same as so what is this? This is T of m tensor n on the left hand side. Right hand side was fm tensor gm. Okay, so we have shown the existence of a unique map which satisfies this property, in other words, which makes the diagram commute. Okay, good. So that proves the proposition. Now let me just say something about notation. We usually denote, so here is a word on notation. We usually denote this map T by the symbol f tensor g. Okay, so this is sometimes confusing with the tensor symbol and so on, but f and g here are maps, so it's it doesn't cause confusion with things of the form m tensor n. So these here are maps. So when I write f tensor g, what I mean really is the unique map T which is given by this proposition. Okay, good. So now there always exists such a map. Now why are we doing all this in some sense, or where does all this fit? So here is a remark on categories and functors and where all this fits in that framework. So observe that well, in some sense the tensor product can be thought of as follows. It's like, so okay, so let me define a category C. So the objects of this category are pairs of objects. So what's a typical object in this category? It's a pair m comma n, where m is a right R module and n is a left R module. Okay, this is like a product category if you wish. You take the right modules as a category, the left modules as a category, and what I'm forming here is really their product category. Okay, and the arrows now, so these are the objects, and the arrows are again the arrows as you would have in a product category, which is I take a pair mn, and what's an arrow to another object in this category? An arrow is just a pair of arrows. Okay, so an arrow is a pair of arrows fg, where what is f? F goes from m to m prime. F is an arrow from here. That is an R linear map, and similarly G is an R linear map from n to n prime. Okay, so these are the objects and the arrows in this category, and what we are just saying right now is that the tensor product can be thought of as, well, it's at least it's the following. It takes objects in this product category C and maps it to objects in the category of Z modules. So here's this is the category on the other side of Z modules. Okay, now what is this tensor product map? It takes this pair mn and maps it to m tensor n over R. Now what we have just shown, so this is the tensor over R tensor over R map. What we have just shown is that in some sense it's also a functor. Okay, meaning, well, we still have to prove it, but it not only does it map pairs of objects to an object there, it also maps arrows to arrows. In other words, if I take another pair n prime in C and I take an arrow between them, okay, but what's an arrow? An arrow is actually a pair of arrows from m to m dash and n to n dash. Given such an object, given such an arrow, what we have just shown is that there exists an arrow between m tensor n and m prime tensor n prime. And this is that map which we call f tensor g. Okay, so not only does this tensor product construction map pairs of objects or objects in this product category to Z modules, it also maps arrows in the category C to arrows in this category of Z modules. Okay, and what's more, this is actually a functor. Okay, so claim there is more. This is actually a functor. from this category C to this category of Z modules. Okay, now recall the definition. To show that something is a functor, you need to show, well, more or less two things, that it respects the composition of arrows, and it respects the identity arrow. Okay, in other words, so let's show that it satisfies the two axioms of a functor. So firstly, we need to show compositions are respected. Okay, so proof A. So let's take compositions. So maybe we'll go to the next page. So first I need to show that this, we need to consider compositions. So if I take M cross N, let's draw the same diagram as before, M prime tensor cross N prime. So if I have, I mean, this is the arrow, this is the one which takes Mn to Fmgn. Okay, and suppose I have another one like this, M double dash cross N double dash. Okay, and I have another arrow which is, it takes M dash cross N dash to let's say A of M dash comma B of N dash. Okay, it's again an arrow in the product category. Then observe that if you compose the two, so what do you get when you compose these two guys? So the full composition does the following: it takes Mn and maps it to just the composition of A with F. So it's A of F of M, this is the composition of A with F, B of G of N. Okay, A and B here are maps. Okay, so it's just the composition of these arrows. Okay, now recall how those things work at the level of the tensor product. So whenever I am given an arrow, so let's do the vertical ones first. So given this arrow from M cross N to M dash cross N dash, we said, well, that defines a map between, okay, similarly there is a map like this. Okay, so this is the map F tensor G, that's the map A tensor B. Now what we need to show that this is a functor, the first thing we need to show is that if instead you take the composition of these two arrows in the beginning, which means you look at AF and BG as your new maps from going from M cross N all the way to the other end, M double dash cross N double dash, then the corresponding map that you define here, so what would that be called? That's called A composition F, so which I'll write as AF tensor BG. Okay, so we need to claim, well, we need to show that this AF tensor BG map is the same as what you would get if you composed F tensor G and then A tensor B. Okay, so that's the first axiom we need to check. So let's check that. AF tensor BG, this map, is it the same as F tensor G composed with A tensor B? Okay, now to check a thing like this, it's actually enough to check it on the generators, right? They're both Z linear maps from, they're both maps with the same source and the same target. So you just need to show that both maps agree on the generators. So check on the generators. So what are the generators? Well, we'll just take the ones of the form M tensor N. Let's just check it on these decomposable tensors. Okay, so let's apply the left hand side on those guys. If you take the left hand side and you apply it on M tensor N, then by definition this is just AF of M tensor BG evaluated on N, which by definition is A acting on F of M tensor B evaluated on G of M. Okay, now let's apply the right hand side on M tensor N. Observe this is again by definition A tensor B evaluated on, again that's A on Fm tensor B of Gm. Okay, so which is obviously the same. So the left hand side and the right hand side are exactly equal. Similarly, so we have checked the first property for this to be a functor. The second property is that it preserves identities. So that's the second thing we need to check. So what that means is, if I take m cross n, okay, from m cross n to m cross n, if I take the identity arrow, okay, so what is the idea? It should map identity objects, identity arrows to identity arrows. So what is the identity arrow in this category C? Well, it's easy to check. It's just the identity on M, comma the identity on N. It's the pair which just takes Mn back to itself, right? This is the identity arrow. Okay, so given this, what's the corresponding arrow on the tensor product side? In other words, what is this? So let's check. What is this? Is this just the identity of the element ident? Is this just the identity arrow on M tensor N? That's the question. Okay, so let's check. So let's evaluate again on the generators. That's all we need. So identity M, tensor identity N. By definition, on a generator just gives me which is just M tensor N, which is therefore just the identity map evaluated on M tensor. So therefore we have again shown the identity axiom. So this is also true. So identity axiom is true, the composition is also respected. Therefore what we have is that this is a functor. So proved. So that's really the point here, that the tensor product is actually a functor from the category whose objects are pairs M and N of right and left modules over R, from that to the category of Z modules.